All right, hi folks, this is Larry Mussolino. I wanted to record a video for Objective 12 in Alex. And Objective 12 has to do with adding or subtracting these radical expressions. It means you might want to add or subtract square roots or cube roots. So first, let me start off by just reminding you about working with square roots. So, if we take the square root of a number like 64, it's asking us what number times itself equals 64, and that answer is 8. So, sometimes we list out perfect squares. Perfect squares are those numbers that represent a number times itself. So 4, 9, 16, 25, 36, and so on. We call these numbers perfect square. Because if I take the square root of 4, I get the answer 2, the square root of 9, I get the answer 3, and so on. If you go to the reference packet and go back to the back of the packet and look at the multiplication table, you'll notice that these perfect squares are listed on the diagonal of that multiplication table. All right, but sometimes we might want to take the square root of a number that's not a perfect square. 20 is not a perfect square. But here's what I'd like to do to simplify this. So we want to try to simplify an expression like this. Well, one thing I could think about is if I have the square root of a times b underneath the square root symbol like this, I'm allowed to break it up to be two separate square roots. So if I have the square root of 20, here's what I'm going to think about. Let me try to break this up as one number times another number, where I'd like one of these numbers to be a perfect square, if possible. Might not be possible, but I'd like to try and have one of these numbers be a perfect square. And remember, the perfect squares were the numbers like 4, 9, 16, 25, 36, 49, so on. Well, I know 20 can be written as 4 times 5, and 4 is a perfect square. Well, now, according to this property, I can break this up to be the square root of 4 times the square root of 5, two separate square roots like this. And of course, the square root of 4 is 2, so I can write this as 2 square root of 5. I know to stop. This is as simple as I can get it because the square root of 5 can't be simplified any further. There's no perfect squares that would evenly divide into 5, so that's the answer for square root of 20. All right, well, let me give you some examples of working with variables. Let's say I had x squared times x squared, or x to the third times x to the third, or x to the fourth times x to the fourth. Well, you probably remember the property that says you have to add the exponents in this kind of a scenario. So this is going to be x to the 4, this is going to be x to the 6, this is going to be x to the 8. So if I take the square root of x to the 8, that's really asking me what quantity times itself equals x to the 8. Well, I could see here from our example, x to the 4 times x to the 4 equals x to the 8. So the square root of x to the 8 is just x to the 4. And you might be able to imagine that when you take the square root of x to an even exponent, when you take the square root, it's really going to take that exponent and divide it in half. So the square root of x to the 20 is going to be x to the 10. The square root of, let's say, x to the 12 is x to the 6, and so on. All right, well, now we can work out this example, because I'm going to break this up into two separate square roots. I'm going to break it up to be the square root of 20 times the square root of b to the 8. But the square root of 20, we worked this out to simplify it. We ended up with 2 square root of 5. And the square root of v to the 8, again, you can think of that as what quantity times itself equals b to the 8. The answer to that is b to the 4. So this is the answer that Alex is looking for. Okay, so the game plan here is going to be to try to simplify the square root of the number and then try to simplify the square root of a letter. Let me give you one more example. What if I had the square root of x to the 9? Well, I know that, if I have x to the 4 times x to the 4, that's x to the 8. And if I had x to the 5 times x to the 5, That's x to the 10. So x to the 9 is not a perfect square. But what I could do is rewrite x to the 9 as x to the 8 times x to the 1. Because I'd like to get an even exponent, because an even exponent means it's a perfect square. So now I'm going to break this up to be the square root of x to the 8 times the square root of x to the 1. I'm just going to write that as the square root of x. The square root of x to the 8 is x to the 4. And the square root of x I'm just going to leave alone. So I can simplify the square root of x to the 9 to be x to the 4 times the square root of x. So if you're taking the square root of x to, let's say, an odd exponent, like 17, for example, what you do is rewrite it as x to the even exponent times x to the 1. Right? Because if it's odd, like 17, I can always write that as x to the 16 times x. Then you break it up into two separate square roots. The square root of x to the 16. Remember what happens when you take the square root of x to an even exponent like that? It ends up dividing the exponent in half. So that's going to be x to the 8. And then just bring down the square root of x with you. And that lets you simplify this kind of expression. Okay, so let's do another Alex topic. How about if we go here, and this one is simplifying a odd exponent. All right, well, again, you're allowed to break this up into two separate square roots. I'm going to do that. I'm going to break it up to be the square root of 49 times the square root of y to the third. Well, I know the square root of 49 is 7. Now, for the square root of y to the third, remember, you'd like to get y to an even exponent out of that. So I'm going to rewrite y to the third as y to the second times y to the 1. Now, I'm going to break this up into two separate square roots. It's going to be the square root of y to the 2 and just the square root of y. But the square root of y to the 2 is asking you what quantity times itself equals y to the 2. Well, that's just y. Bring the 7 down and bring the square root of y down. So that's the answer. Again, remember, anytime you take the square root of a variable to an even exponent, like 50, let's say, what you end up doing is dividing that exponent in half. So the answer would be y to the 25. All right, let me do another one. Why don't we talk about adding and subtracting? Let me do a different example first, then we'll come to that one. All right, let me do an example where we're adding or subtracting these square roots. Well, it turns out when you are adding square roots, you can almost think of the square root part as like a like term. So let me give you an example. How about if I had 10 times the square root of 2 plus 7 times the square root of 2? Well, I'm always going to think of this as like 10x plus 7x. So I'm going to keep the square root part as is, bring it down, and then I'm going to add these numbers in front together to give me 17. So it's almost like you're adding together like terms here. It would be the same thing with subtracting. Let's say I had 8 times the square root of 3 minus 4 times the square root of 3. I would keep the square root of 3 part as is, and then work out 8 subtract 4, that's just 4. Now, what if you have different square roots? What if I had 10 times the square root of 2 plus 7 times the square root of 5? Well, for this, you cannot add. I would just have to leave this alone. I can't add. I can only add when the square root parts are exactly the same. Because this is square root of 2, this is square root of 5. These are different. That means I can't add these together. This would be like trying to add 10x plus 7y. Well, those are unlike terms, so I can't add them. All right, well, let's go to this example. I'm noticing there's the square root of 11. So that's the same square root part. So I'm going to keep the square root part as is and subtract the numbers in front. 5 subtract 4 is 1. Usually we don't write the number 1 in front, so usually we'll just write this as the square root of 11. Okay, so let's do a few examples of adding and subtracting square roots, and then we can also talk about adding and subtracting cube roots as well. Let me try an example here. All right, so they want me to add or subtract these 3 different square root expressions. Well, I'm noticing the square root parts are all different here. Right, here's square root of 75, here's a square root of 3, here's a square root of 12. So I really can't add these because the square root part is not the same. But what if I try to simplify these first? So let me try to simplify them. All right, let's work out 4 times the square root of 75. And then we'll work out these other parts. Well, remember, the idea is take 75 and try to write it as the multiplication of 2 numbers where one number is a perfect square. Remember, the perfect squares are numbers like 4, 9, 16, 25, 36, and so on. Well, I know 75 I can write as 25 times 3. But I'm going to break it up to be 4 times the square root of 25 square root of 3. But I know the square root of 25 is 5, so this is 4 times 5 times the square root of 3. But 4 times 5 is 20, so this is 20 times the square root of 3. All right, well, I'm just going to bring this 10 square root of 3 down with me because now I do have the same variable parts here. Excuse me, I have the same square root parts. I have a square root of 3 and a square root of 3. All right, let me come over to the square root of 12. And I want to rewrite 12 as a multiplication where one of the numbers is a perfect square. Well, I could use 4 in this case because 12 is 4 times 3. All right, break this up into 2 square roots. The square root of 4 is 2. So this is 2 square root of 3. Now I can combine these because now I have the same square root part in each of these expressions. So I keep the square root part as is, and then I'm going to do 20 plus 10, that's 30. 30 minus 2, 28. So the answer to this one is 28 times the square root of 3. So even though it didn't look like I could add or subtract these because the square root parts were different to start out with, it turns out that by simplifying each one of them, they did end up all reducing down to have a square root of 3 part in them. Okay. All right. Let's do a few more. How about if we do an example here? And now this has a cube root. All right, well, let's talk about perfect cubes because we're going to talk about cube roots now. So we need to talk about perfect cubes. First, let me talk about numbers. A perfect cube is a number that represents some number times itself 3 times. Let me write out some perfect cubes. 2 times 2 times 2. Well, that's 8. 3 times 3 times 3, that's 27. 4 times 4 times 4, 64. 5 times 5 times 5 is 125. So these are perfect cubes. Okay, so I'm going to be on the lookout for these numbers. Let's go to variables. What if I had x times x times x? Well, that would be x to the 3rd. What if I had x squared times x squared times x squared? Well, that would be x to the 6th. X to the 3rd times x to the 3rd times x to the 3rd. Remember, this is where you add the exponents, x to the 9. So if I worked out the cube root of x to the 3rd, That's asking me what quantity times itself 3 times equals x to the third. That answer is just x. What if I worked out the cube root of x to the 6? Well, that's asking me what expression times itself 3 times equals x to the 6. Well, I can see here the answer is x squared. And let's do the cube root of x to the 9. Well, you can probably see the pattern here. I'm taking the exponent and dividing it by 3 to get the answer. Because if I take 6 divided by 3, I get this exponent 2. If I take 9 divided by 3, I get this exponent 3. So these are going to be the perfect cubes when it comes to working with cube roots. All right, so let me come over to this example then. It's the cube root of x to the 4. Well, what I'd like to be able to do is write this as a perfect cube times something else. Well, I know one of the perfect cubes is x to the third. So I'm going to rewrite x to the 4th as x to the 3rd times x to the 1. Okay, I'm going to break it up into 2 separate cube roots. But the cube root of x to the 3rd, we said earlier, was just x. So this is x. The cube root of x, I can't do anything to simplify, so I'm just going to bring that with me. So this is the answer to simplify this example. All right, let me do a few more examples here. All right, why don't we take a look at this one? And again, they're asking us to simplify this. So they're asking us to add or subtract. In this case, it looks like it's a subtraction. And you might say, well, wait a second, we can't subtract these because the square root parts are different. Yes, they're different right now, but first let's try to simplify and see what happens. All right, so let me take this first square root and I'm going to try to simplify this. Whoops, I wrote that wrong. Let me erase that. Okay, so let me do this. I'm going to take and break this up to be the square root of 72 times the square root of z to the 3rd. Let me try to simplify each one of these separately. Well, the square root of 72, I know 72 is not a perfect square, but can I write this as some number times another number where one of the numbers is a perfect square? Well, yeah, I can write 72 as 36 times 2. Then I'm going to break this up to be the square root of 36 times the square root of 2. But I know the square root of 36 is 6. So that's 6z times 6 times the square root is 2. All right, let me keep going because now I want to look over here at the square root of z to the 3rd. Again, I want to break that up to be a perfect square times something else. Well, I'm going to write that as z squared times z. Now I'm going to break this up into 2 separate square roots, the square root of z squared times the square root of z. Well, the square root of z squared here is just z. So it's going to be z times the square root of z. I got to be careful because this is a 2 and this is the letter z. Sometimes I put a little mark like this to make it clear it's the letter z. All right, so here's what we have. It looks like we have 6 times 6, that's 36. We have a z and a z, so that's a z squared. And then we have the square root of 2 and the square root of z. All right, let me come over to this side. I'm going to do the same thing. I'm going to break it up to be the square root of 18 and then the square root of z to the 5. Let me look at the square root of 18. Well, I can break that up to be the square root of 9 times 2. That's going to be the square root of 9 times the square root of 2. I know the square root of 9 is 3, so that's 3 times the square root of 2. Now let me go over z to the 5. I want to break that up into be a perfect square, and I could write z to the 4 times z to the 1. Break this up into 2 square roots. Well, the square root of z to the 4 is z to the 2. All right, well, let me put all this together now. I'll write it up here maybe. I'm going to take this expression and I'm going to put the 2 and the z together underneath one square root. So I'm going to combine these under one square root. So we have 36z squared times the square root of 2z. That's this part. And let me come over here. It looks like we have a 3z squared. And again, I'm going to put the square root of 2 and the square root of z together underneath one square root, square root of 2z. Well, notice we do have the same square root parts now. These are the same. So we can combine these. So I'm going to keep the square root of 2z as is, and I'm going to do the subtraction in front. This is 36z squared minus 3z squared. Well, those are like terms. That works out to be 33z squared. So this is the final answer for this question. All right, so this is a little tricky, but again, we had to try to simplify as much as possible. And once you simplified here, you did end up with the same square root parts, which meant you could do the subtraction on it. All right, let's see. We haven't done any here. All right, so on this one, if I'm going to take the 5th root, notice this is the 5th root. If I can get this to be y to the 5 underneath, the 5th root of y to the 5 is just y. So here's what I'm going to do for our example. I'm going to take y to the 6 and rewrite it as y to the 5 times y to the 1. Now I'm going to break this up into two separate 5th roots. It's going to be the 5th root of y to the 5 and the 5th root of just y. The 5th root of y to the 5 simplifies just be a y. And then this 5th root of y, I just bring down with me. I can't do anything to simplify it. So this is the final answer on that one. Okay, let's see here. Which ones haven't we done yet? Let's do this one. I don't think we did this one yet. Okay, so again, what I'd like to do is break this up into two cube roots. So I'm going to separate this to be the cube root of 8 times the cube root of y to the 7. And I'm going to try to simplify them separately. Well, I know that 2 times 2 times 2 equals 8. So that tells me the cube root of 8 is just 2. So this result is just a 2. All right, I also know that when it comes to perfect cubes, if I could write something like y to the 3 or y to the 6 or y to the 9 or y to the 12, these are all perfect cubes. But I don't have y to the 6, I have y to the 7. But what I'm going to do is rewrite y to the 7 as y to the 6 times y to the 1. Then I'm going to break this up into two separate cube roots. But the cube root of y to the 6 is asking you what quantity times itself 3 times equals y to the 6? Well, that answer is y to the 2. You might remember the shortcut is you could take this exponent 6 and divide it by this 3, and that gives you the answer y to the 2. Bring this 2 down with me, bring this cube root of y down with me. So this is the final answer for this example. Okay, I think, let me just see this. Did we do this first one? No, we didn't do this one because this has several variables underneath. All right, well, even though there's 2 variables here in this problem, I'm still going to set it up the same way. The first thing I'm going to do is let me break this up into separate square roots. Square root of 20, square root of x to the 7, square root of z to the 3, and I'm going to try to simplify each one of these separately. All right, well, 20 I know is not a perfect square, but can I rewrite it as a perfect square times another number? Well, yeah, 20 I can write as 4 times 5. Then I break it up into 2 separate square roots, but the square root of 4 is 2, so this is going to be 2 square root of 5. Okay, let me go to square root of x to the 7. Remember, when you have an odd exponent, you want to write it as an even exponent times x, like this. So I'm going to rewrite x to the 7 as x to the 6 times x to the 1. Break this up into 2 separate square roots. The square root of x to the 6 is x to the 3. I got to bring down the square root of x with me. Let me come over and do this last one. I'm going to break this up to be z to the 2 times z to the 1. Break it up into 2 square roots. The square root of z to the 2 times the square root of z. But the square root of z squared, well, that's just z. And the square root of z I just bring down with me. Okay, this is the answer. If you wanted to, you could combine these 2 square root parts, put it under 1 square root if you wanted to. So I could write it as xz. And then I'm going to write the rest in front. 2 square root of 5, x to the 3, and a z in front. So this is the final answer for this example. Okay, hope this is helpful as you're working in Objective 12. Please remember to make use of the help resources in ALEKS. You have the explanations and you have the videos. So please try to make use of those as much as possible.